Good morning. Here we are at the physics video lecture once again. Physics 105A video lecture 22. So I had a couple of questions about some of the older problems. Perfect time to review them actually. The exam has been postponed for a few days. Nothing wrong with that. And so the first problem, there were three problems that I'm going to talk about. We'll see how much of the hour it takes, doesn't matter. These are great problems. So the first one is the oscillation machine. Okay. So we had springs. Here's our x-axis. So we're connecting springs to this mass right here, this mass M. And then hooking, connecting them to the mass and hooking them up here. So we have these springs, ordinary spring constant K type of springs. They have a relaxed length of L, and this frame has a length of 2 times A. So it's A from here to here and down to there. So spring, let's go ahead and say spring K, relaxed length L, less than or equal to A. Okay. So if it's less than this fixed length A, then you actually have to hook them and stretch them a bit for this mass, to get this thing going. This is the top view, and then if you pull this thing to the right, it has a restoring force to the left. Push to the left, it has a restoring force to the right. And what we want is the potential energy of this thing. So we stretch this thing out here a bit. Maybe I'll use another color. We stretch it out here a bit, and now it's here. And we're naming this point X as well. And we want the potential energy as a function of X. It'll have a minimum here at the origin, and as we stretch it, it will increase. Okay. And just by the construction, we see the thing is symmetric with positive and negative X. Okay, so what do we have here? This spring is stretched, so the potential energy, let's just construct it. There are 2 of these springs. I'm just going to multiply by 2. And then we have 1/2 K. And then how much this thing has been stretched. Okay. So it's been stretched. Do this all at once. So what do we have for the length of the hypotenuse here? Length of the hypotenuse is square root of x squared plus a squared. Okay. We've got 1/2 K, and we've got that length. I'm just going to write capital L of x minus L squared for the first try at this thing. Okay. Because it's that amount that it's been stretched squared that stores the potential energy in the spring. So now we can put it into a standard form. And I'll pull the 1/2 out. Got the 2K. And then we're going to square this thing here, so that is square root of x squared plus a squared minus L, the quantity squared. So that's the potential energy function. And it has a little bit of interest there. So in order to make further progress, we had to expand this thing in a Taylor series. And this is really the perfect example for an expansion. So I'll take the opportunity just to talk about these things in general. So potential energy functions. Let's just do a graph of some generic potential energy function that has what we're looking for, namely a local minimum here at x sub 0. What we're after is to find the parabola that would just nest in that curve. Okay. The first thing we do is take the function and shift the origin. Once we discover where x0 is, we can shift the origin. So for example, our contraption up here is something like this, except it has its local minimum at x equals 0. So what we would do here is expand u of x0, u prime of x0, x minus x0, u double prime, x minus x0 squared. And there can be higher terms as well. Since we're at a local minimum, that one vanishes. x0, this is local minimum. And this is just a constant. And this is the one that is going to be important for harmonic oscillations. If the second derivative vanishes, though, you actually have to go up into higher order terms, and you don't get harmonic oscillations anymore. This is the one that gives you a Hooke's law type of term, of force. Okay, so that is the program for our u of x up here that I've just generated. For our example above, what do we have? We have u of 0. Easy enough to find. We have 1/2, 2 cancels, so we have k. And then 0 squared, so we have square root of a squared is a, so just a minus l. So we have k, a minus l, the quantity squared, okay? But that's just a constant, doesn't really mean much for the dynamics. Let's take two derivatives. U prime of x, we've got the 1/2 of the 2k now this thing here, to take its derivative, we have to go first 2 and then root x squared plus a squared minus l to the first power. And then this is something to the 1/2 power, so we have 1/2 root x squared plus a squared, and then the inner derivative is 2x. So this one is worth cleaning up a bit. Okay, we got a bunch of cancellations, but this time we actually have to make sure we keep the number there. So we have 2k, these cancel. And we can divide through here, so we would have 1 minus L over root x squared plus a squared. And then we've got an x, okay, right there. So as we saw from the construction, this vanishes at x equals 0. As had to also be the case here. Let's do another derivative. Do that right here. So what about the second derivative? The second derivative, we've got 2k. We're going to just differentiate that x out of there. We have 2k, 1 minus L over root x squared plus a squared plus, and now, since we're going to have I'll just write 2kx, and when we differentiate this object here, we're going to bring out a 2x again. So what we know is, I'm just going to put dot, dot, dot. We know that when we evaluated x equals 0, this is all that remains here. So let me go ahead and write here in red, just for the heck of it. We have u prime of 0 is equal to 0. And over here we have u double prime of 0 is equal to 2k. And then we're evaluating at 0, 1 minus L over a. Or I can rationalize that denominator. I'll have a minus L divided by a. A minus L divided by a. So there's our second derivative, and there's a lot to discuss right here. First thing, the first thing I'm going to do is write out our function. I'll keep that picture and just erase these expressions here so I have some board space. So what does our expansion look like? We have u of x is equal to a constant. I'm just going to write c, that doesn't bother us. And it's 1/2 u double prime of x0, etc. So 1/2, and then there's a reason to keep the 1/2 out here. So then I'll have this 2k a minus L over a. And then we have the x squared. This is an effective spring constant, so we can call this k effective. Yeah, effective spring constant. And it's an E, effective. So yeah, it has the same form, and we can ditch the C and just shift our origins, shift everything. But yeah, we have a constant that we just already discussed, and we have 1/2 times this something positive quantity, which is of course the second derivative evaluated at equilibrium. So that's interesting, and you could just call it K effective, and then as you pursue this, you say, well, we just have harmonic oscillations now, right? As soon as you have this, you have a mass, you have an effective spring constant, you have harmonic oscillations. So you don't have to go any farther than this. You can say, okay, harmonic oscillations because we've gone through that theory several times with omega squared equals K effective over M. Okay, so that's the first thing. But we have this really interesting case here, because if the spring happened to have the relaxed length equal to A, then everything changes. Okay. So as long as the spring is shorter than this frame length A here, if the spring is shorter than that, then you have to stretch it to install this system, and then you get this second derivative. But if A equals L, the second derivative vanishes, you no longer have harmonic oscillations. You would actually have to go past the third derivative to the fourth derivative, which is, if you have some time, you can try it. But you have to go to the fourth derivative, and then your function is going to have the form u of x is equal to a constant, which is irrelevant, plus some number times x to the fourth. That'll be your leading term. That doesn't give you harmonic oscillations. Really important point. So that's why this machine here is the perfect example to teach a lot of these things. So I'm going to put that down as an important note. So I'll even number these things. 1 and 2 here. If L is equal to A, then U double prime of 0 equals 0. Then your leading term would be the fourth order term. Okay. Because this thing's going to be symmetric, the third derivative term is going to vanish. Okay, you can be sure of that. And then you're going to end up then U of x equals c plus, I'll just write u to the fourth derivative of 0, 4 factorial, x to the fourth, plus and so on. Okay, it's an important comment, even though it's right here in the lower corner of the board. And no harmonic oscillations. Okay, they're not going to have a trigonometric solution. There will be oscillations, they won't be harmonic. Okay. Double exclamation. Okay, so yeah, this is a system that you can really study and learn a lot. Thinking about it. And remember, I'll even put this here. This as a bubble here. So recall our discussion. You can look back in your notes of u of x equals b x to the nth power. So we had that general function x to the nth power, and in this case, our next approximation would be the fourth power, n equals 4. So here we have n equals 4, but not n equals 4 all the way. It would be just the leading term. Then we would have a 6th power and so forth and so on. Okay. So yeah, you really come to appreciate the harmonic oscillations, the second derivative being positive, because in a problem like this, once you do your expansion, locate the value, find the value of the second derivative, you're done. Okay. Good. So that was one problem that's worth reviewing. The next one was about Eulers' formula. Actually, these two problems that I'm going to talk about now, they would help us segue right back into our Fourier integration, which is what we're about to start doing, our Fourier series. So yeah, this next one was about the Euler formula. Let's go ahead and talk about that. Yeah, I thought I had put pretty much everything there, but let's go ahead and go through the whole thing systematically. That's an important one. So we have from Euler, imagine how great it is to discover these things. Okay. But learning about them is also great. What do we have? E to the I theta cosine theta plus I times the sine of theta. And the way we want to prove this, excuse me, we want to prove this, and the way we do that is do all three of these expansions. So let's just look at our Taylor expansions for e to the x, cosine x, and sine of x. For all of these, we're looking at f of x is equal to the sum k equals 0 to infinity, kth derivative. In this case, we're expanding them all around 0. So kth derivative at 0 divided by k factorial times x to the kth power. And what you find is, you find e to the x is equal to 1 plus x squared over 2 factorial x cubed over 3 factorial all the way out to infinity. Because if f of x is equal to e to the x, f prime of x is also equal to e to the x, etc. So evaluated at 0, we just get a bunch of 1s, and then 1 over k factorial times x to the k. So that's the series expansion for the exponential function. What about the sine and the cosine? Let's go ahead and erase this. So yeah, we had the definition of or we know the exponential function as a function whose derivative is the same as the function itself, okay? And we had our Taylor expansion definition, so we just go right in here, and there's our exponential expansion. How about f of x equals sine of x? We have f prime of x is equal to cosine f double prime minus sine third derivative minus cosine. Okay, and the fourth derivative, sine. Okay, so we start with sine of x, cosine minus sine minus cosine, sine. Okay, and then it just repeats itself indefinitely. So from this we get sine of x is equal to x minus x. Oh yeah, when we evaluate these things, the second derivative vanishes. The fourth derivative vanishes, okay? And otherwise we just get plus and minus 1. So we get this alternating series, minus x cubed over 3 factorial, x to the 5th over 5 factorial, and so on. And then cosine of x is going to be 1 minus x squared over 2 factorial, which is just 2, minus x squared over 2, plus x to the 4th over 4 factorial, and so on. Okay, so that's how we get those systematically. And now, instead of x, we go ahead and use I times theta for our exponential. Okay. Now, for e to the I theta, we have see, what do we have here? E to the I theta is equal to, we already have, we can just replace x with I theta, okay? So we have 1 plus I theta plus 1/2 I theta squared plus 1/3 factorial I theta cubed, and so on. And we get, I'll continue it over here on the right, we get 1 minus, see, I squared is going to be minus, so minus 1/2 theta squared, plus and so on, plus I times theta, and then I cubed is going to be minus I, okay? Because I squared is minus 1 times I, so minus I, and so on. You do a few more of these, you see the pattern. This is the cosine, 1 minus x squared over 2, it keeps going. And this is the sine, theta minus theta cubed over 3. So yeah, if you want to really make it clear to yourself, go out a couple more and you'll see it without any doubt at all. So yeah, that means we really own this thing. This is, and we're making a lot of use of it, so this is of course an expression you really want to understand. So that's how that went. Okay. So this time around we got our Taylor expansions, okay, for all three of these, and then we evaluate the left side of this and we find out, sure enough, cosine theta plus I sine theta without those substitutions. Good. And that took us to the last question. Let me consult the clock here. We've got nothing but time. Very well. The last question that came up was that nth root of -1. This one's a lot of fun. So yeah, let's go ahead and look at this e to the I theta now. Since it's cos theta plus I times the sine of theta, if we just go to the complex plane and just take any old complex number here, there's an angle theta, and we can see we've got the real part, cosine theta. Okay, so this is on the unit circles as a length 1. This is cosine theta, and this is I times sine theta. So yeah, that complex number has an expression, or can be expressed as cosine theta plus I sine theta. And then it turns out that that's just e to the I times theta, right? So now, suppose we have, now consider, so now consider z to the n equals -1. That is the same as saying e to the I, I'll say phi, to the nth power. Well, I could use theta. Why change right now? So e to the I theta to the nth power is equal to e to the I times pi. This is the key here because -1 is e to the I times pi. Where is that? -1 is over here. No. Here's our unit circle, right? So if this is 1, -1, theta is equal to pi. So this is the key to that problem. E to the I theta times n to the nth power, or e to the I times n theta is equal to e to the I pi. Now the question is, when does this happen? Okay. For what values of theta does this happen? It happens when n times theta is equal to pi, okay, or 3 pi. In other words, if you go around here, you're at pi. If you go around again, you land there again, 3 pi, 5 pi, etc., depending upon how large n is. So now you just have to work out an expression so starting with an n, and I think we can do it this way. N times theta is equal to so we're gonna get an index here. We're gonna have n minus one of those solutions, okay? Or we're actually gonna have n solutions altogether. So pi times 2k plus 1 is going to do it, okay? Pi times 2k plus 1, k equals 0, 1, 2, all the way to n minus 1. See, so that's going to do the trick. Divide both sides by n, and then you have theta, okay? And what you want to do is test this for, say, I'm going to set this up. You want to test this formula for n equals 2, n equals 3, n equals 4, where they're easy to draw. Okay. Let's go ahead and test it for n equals 4. So example. N equals 4. Theta equals, well, let's go ahead and write pi 2k plus 1 divided by n. K equals 0, 1, 2, 3. So theta is going to equal pi over 4 times 1, pi over 4 times 3, pi over 4 times 5, pi over 4 times 7. 1, 3, 5, 7. Now let's locate those on the unit circle. Okay, so here's the unit circle, pi over 4. Okay, 3/4 pi right here. And oh, let's do it. Pi over 4, you multiply this angle by 4. 1, 1, 2, 3, 4. You'll land right there. 4 times 3, 5, 7. So those are the roots, the fourth roots of minus 1. So yeah, this is a good one to play around with. And yeah, it's just a nice, this is an interesting equation. But the last thing, this counterclockwise business turns this into a circular motion machine, okay? So if instead of e to the I theta, we have e to the I omega t, what we're talking about is a point in the complex plane that's just uniformly going counterclockwise. Okay? So that actually segues very nicely into e to the, z equals e to the I omega t. And you've got that relation of uniform circular motion to harmonic oscillations. And you can say that's the secret of this function here when we're talking about oscillations. Okay? Now we just let, omega is a frequency, t is a time, and if t runs, then, right, this dot is just doing the counterclockwise motion in the complex plane. The projection onto the real axis is our cosine omega t and so forth. Okay, good. Yeah, we're not going to do much more in this hour. I'll take us back into what we did last time and pretty much leave it there. But it's a good progression, and yeah, you definitely want to get to know these numbers and how to operate with them. Good, so we use this to solve the linear differential equation with constant coefficients. And we use that for our oscillations, our driven oscillations, our damped oscillations. So it's the natural function. To use in all these cases. I've heard it said once that nature calculates with complex numbers, okay, and seems to be the case. So let's look at our Fourier series. That'll just bring us up to where we were last time, and we'll pick up with that in the next lecture. Because this is what we had now obtained. So for I'll just title this Fourier series. Fourier series. When you look this up, you'll see that there's the real Fourier series, the complex Fourier series. We're going to generate all of it, but the way we started with the complex function is the easiest way, the clear way, the best way. So Fourier series, we're looking at functions that are periodic, 2 pi periodic, and we're going to choose the interval minus pi to pi. We're actually talking about real functions now, and we're expanding them with these complex exponentials. So really anything you can, right, this one, yeah, I'm always choosing a bad one, but if this were a periodic function, then it would start again over here and do what I just did. Okay, I can't duplicate that. I should start with something a little easier, right? But yeah, periodic functions, 2 pi periodic functions. And you can also just say, well, we're only interested in functions between minus pi, and we just continue them on periodically. These discontinuities are actually an interesting thing. What's going on right here? Okay, so we can talk about that later. Don't worry about it. For now, actually, we could just restrict ourselves to truly continuous functions if you want, but not for long. Okay, so 2 pi periodic functions. What we have is f of x can be expanded in a series expansion of these functions here, e to the I kx, where k are just integers, all of the integers from minus infinity to plus infinity. And if and when this is possible, the coefficients are simply given by 1 over 2 pi integral minus pi to pi f of x e to the minus I k x dx. That's what we showed last time, and I'll refer you to that calculation that we did. You should have a look at it and make sure you understand it. It's canonical and it's it's basic. It's not hard, very important. So yeah, we have this type of expansion. It's very important because you're essentially expanding something in sines and cosines. Now, I'll just write down the example I'm going to calculate next time. So next time, we're going to study this function here. F of x is equal to minus 1 from minus pi less than x less than 0 and positive 1 from 0 less than x less than pi. Okay. Notice these open intervals here. If you graph this thing, what does that look like? You go minus 1 to plus 1, and then, 1, 2, 3, 1, 2, 3. So pi is right out here. Okay, pi minus pi. So yeah, what does this look like? Negative over here. Positive over here. Yeah, we can do a little better. Okay, here's our function. The other color is actually good to have here because I've got these open intervals, so I'm saying it's not there, not there. And in fact, what you can show is the Fourier series for this step function, with its infinitely steep slope between here and here, actually goes through the origin. Okay? But it's infinitely steep, so it's truly the step function here. So we'll do that next time. It's always pretty interesting to see this function generated out of these functions, and because it's a real function, all of these e to the I kx are going to turn into, in this case, sines. Okay, this cosines are going to drop away. We're just going to end up with sines. Good. Let's leave it there. So this is what we'll do next time. But you guys go ahead and have a good look at how we went from here. How we derived these functions right here, these coefficients. Good. Until then.